Okay, according to the loop control, we classified the CNC machine into two types. We said open loop and closed loop. So this open loop and closed loop is related to the way of control the positioning system. So in order to control the positioning system of the NC machine or the CNC machine, we have two type of control. One we call it open loop, which is no feedback to verify the actual position achieved at the desired is the desired position or not. That means we have a set point or desired position. We enter to the machine or to the controller. The controller send to the drive. The drive move the table, for example, or move the spindle of the machine or the workpiece. Then we don't know if the new position is exact to the programmed position. Okay, the coordinate is the same as the coordinate that we desire. For that we call it the open loop. In the case of the closed loop, we have a feedback that measure the and confirm the final position, um, and this final position will be compared with the desired position. So we have the actual position, and this actual position will be compared with the desired position. So if it is exactly the same, so no need to give any signal. But if it is not exactly the same, so the controller need to take action, either to move it right, move it left, move it up, or move it down to achieve the desired position. Okay, so usually I used to use the analogy of the for the open loop and closed loop by some or one of the existing control system that in our life. As a car driver, for example, if you drive your car while your eyes are closed, that means it is equivalent to the open loop control system. Why? Because when you drive your car, the car will move in the on the road, but there is no feedback taken by your eyes to know if the car is go in the correct path or in the wrong path. For that you may make an accident because there is no feedback taken from the current position or the current location of your car with respect to the route or the correct path that you want to follow. While the closed loop here analogy can be represented by the driver who drives the car or who drives the car with open eyes. So in this case, the eyes of the driver will give the feedback to the driver in order to take the correct decision, okay, and decide if the car is moved at the correct path or not. If not, so he will going to adjust using the steering or using the pedal steering and so on in order to keep the car in the correct position. So this is the difference between the open loop and the closed loop. Usually the closed loop system, when we represent the open loop and closed loop system in the control system, the open loop only represented by using three blocks. This is the general representation for open loop and closed loop. So the open loop is represented by three blocks. One is the controller, the second is the actuator, the third is the process. So there is a set point will given to the controller or to the MCU. Controller will give the signal or the feedback, or the output to the actuator. The actuator will take the decision to convert this signal from electrical into a movement or mechanical action on the process. Then the process will give me the required output. But in the case of the closed loop system, we have one more element here. We call it for the feedback line, and this element actually will be compared with the set point. So this is the set point here, or the desired value, and this is the feedback. So we call it feedback because it's come from the actual or the output of our system and go again to the input of the controller. So this will be represented by using a sensors. So sensors usually will measure, if this system is to control temperature, so this will be temperature sensor. If this system will control the pressure, so this will be pressure sensor. If this system will control the light, So this will be a light sensor. If this system will control the humidity, this will be humidity sensor, and so on. So the type of the sensor here depends on what is the actual value I want to measure. In our positioning system here, the position, I mean the process, or the value that we want to measure here is a coordinate, it is a position. So we need here some a sensor which can measure the position or the coordinates of our or the output of our system. Okay, so in this case we have this, we call it the closed loop. That means you have a sensor which give you a feedback, I mean give the controller the feedback, so the controller can take an action in response to this feedback. If the actual value is equal to the desired value, so the controller is working perfect, no need to do any changes to the output, to the controller, to the actuator. But if the output value is less or more than the desired value, the position is not correct, so the controller need to adjust. So the controller will give a signal to the actuator here. Actuator here in our NC positioning system will be represented by using either servo motor or stepper motor. As we explained before, we explain about the servo motor and what are the main components for servo motor. We said we have servo motor, we have a servo drive, which is an electronic circuit of amplifier to control the servo motor. So here we have either servo motor or we have stepper motor. So servo motor is used for the closed loop control system. Stepper motor is used for the open loop control system. As we can see here, so the stepper motor here uses stepper motor to create movement. So the move will be in steps. Okay, depends on the, we are going to give the desired position, and the stepper motor will give the output to move the axial of the positioning system to the required position. But there is no feedback to know what is the actual value of the system at this moment, for example. So here for the open loop, this is how the open loop system will looks like. This motor here, stepping motor or stepper motor. Okay, so this stepper motor usually run without any feedback. So we have the input is pulse of train input here, pulse of train input here to give the required position that is required from this screw or lead screw. So the motor will rotate and this table will be moved either close to the motor or away from the motor. Here depends on the rotation of the lead screw here. So but there is no feedback to know what is the current position. So how the motor will know what is the current position? There is no feedback to the motor. For that, in this type of system we call it open loop, because there is no feedback. If the position is here or the position is there or here, the motor will not know the exact position. There is no feedback about the exact position at this moment to the motor. We only have input, and we expect from our input that will be made based on some calculation and programming code to send the table to this position. But we are not sure if the table will move to here or not, if the table is moved to this point or not, because we do not have a feedback system. There are some calculation related to the open loop positioning system, or especially to the stepper motor. So usually the stepper motor will rotate, for example, for 300, I mean the one cycle of rotating is 360 degree. So 360 degree will divide it into steps actually, because it's stepper, so it's move in steps. So each step it has angle, so we call it step angle. So the step angle here, or alpha here, is the step angle is equal to 360 over ns. What is ns here? Ns is alpha actually is the step angle in degree, and ns is the number of step angles for the motor. So each motor it has number of step angles. um, if you have 10 for example, so each angle will equal to 36 degree. If we have 100, so each angle will be 3.6 degree, and so on. So am here another formula, which is the open loop positioning control system, or the stepper motor here, all related to the stepper motor, since we are using stepper motor in the open loop positioning. So you need to memorize this, and to understand, you need to understand and memorize this formula, because later on this formula will be used in some of calculation for the examples and exercise. Okay, so for example, here the other formula is am is equal to mp times alpha. Alpha, we said it is the step angle. Am here is the angle through which the motor rotates, so it's in degree, so the angle through which the angle will be rotate. And mp here, our stepper motor run by using train of pulses. So based on the number of pulses, we are going to calculate the value of m. If we know the value of the stepper the step angle and the number of pulses, we can find what is the actual angle of the rotating for this motor. Another example and another formula here is also to calculate the value of a, which is the angle of the lead screw rotations in degree. And rg here, we see the gear ratio. The gear we have, because we have rotating here, this will rotate. How we can rotate this one? It will engage with the camshaft of the motor by using the gear. Also it will engage with the table for the machine by using gear. So here is the gear ratio, and nm is the rotational speed of the motor in revolution per minute, and n is the rotational speed of the lead screw itself. So this is the speed of the motor, nm. Okay, the speed of the motor is nm, and the speed of the rotational, I mean the lead screw, is n only. Okay, so the motor shaft here is generally connected to the lead screw through gearbox. So gearbox is used to couple between, this is for example here there is a gearbox used to couple between the motor and the lead screw. So usually, when we use we can perform some type of calculation on this one to find the value of the angle of the lead screw, and also the gear ratio, the rotation of the speed, and so on. So we need to use these two formula. This is one formula, and this one is another formula. We will see later on some example about how to use these formulas in our calculations. Another formula here is related to the linear movement of the work table. So we set the table here in the open loop. This is the table. The table will move, for example, here to this direction or away to that direction, in order to find how fast or what is the movement, how this table will be moved in a distance based on the displacement by using x, which is the x-axis position here. So the x-axis position will equal to p times a over 360. So x represent the x-axis position relative to the starting point or the starting position in millimeter or in inch, depends on what's the units that we are going to use. Then we have the b here, or the pitch of lead screw, as we mentioned before, either in millimeter per revolution or inch per revolution, or last time we said millimeter per thread or inch per thread, depends. Okay, then we have a over 360 here is number of lead screw revolutions. Why we use 360? Because 360 represent the complete revolution or the complete cycle of revolution from zero to return again to zero. If we have, this is the axis, so if the motor is rotating for, or the rotational axis is rotating for one cycle, so clockwise or counterclockwise, it will be 360. So this will give the number of lead screw revolution. So the number of the pulses required to achieve the specified x position. If I want the table to move, for example, to the position x equal to 5, x equal to 7, there is a specific value for these coordinates of x. Okay, x position increment is given by using the relationship in this formula here. So nb here, we already define mb, or number of pulses, equal to am over alpha, equal to rg over times a over alpha, and so on. Alpha is the step angle. You need to relate between this formula in this slide, also in the previous slide, for the value of angle through which the motor is rotated, which is am, and so on. So all these formula will be used to find the value of the displacement or the movement along the x-axis here, which is represent the movement of the table on the machines on the x-axis. So please go through this formula and try to apply this formula when you use to calculate your either the number of pulses, angle of I mean the angle of here, the step angle, the speed, whatever parameter you want to calculate related to the stepper motor. So you need to refer to these formulas. So also the control pulses here are generated at a certain frequency. So when I want to relate to the frequency, because always the speed of the motor is related to the frequency. So usually either the motor is electrical, I mean any electrical motor which is feed either I mean from the AC source. So we have a frequency for the AC source. So there is a direct and we have a rotation here, so usually there is a direct relation between the speed and frequency. So if n here is the rotational speed of the screw, fp is the pulse train frequency, it's the unit of frequency is in hertz or pulses per second. Ns is the step per revolution or pulses per revolution. Rg is the gear ratio. So this is the formula that relates between the speed and the other parameter of the frequency, steps per revolution, and also the gear ratio. Here also the work table travel speed. What is the speed of the work table that will be travel in the direction for let's grow? So we have Vt, which equal to Vr equal to Mb, which Vt here can be measured in millimeter per minute, in inch per minute, depends on which unit we are going to use. Are we going with the metric system or the system which use inch and other units? Table feed rate, this will be table feed rate, so it will be also measured either in millimeter or meter per minute or inch per minute. Lead screw, so here the pitch with I mean the pitch millimeter per revolution in or inch per revolution. So all these formulas are going to be applied in the coming examples. So this is the first example. Here we have stepper motor that has a step angle of 3.6 degree. That means you have the value of alpha which is 3.6 degree here. How many pulses are required for the motor to rotate through 10 complete revolutions? That means you have the number of revolution are 10 and you have uh, the pulse angle, I mean the step angle, which is 3.6. Then he asked about how many pulses are required for the motor to rotate through the 10 complete revolutions. Then what pulses frequency is required? What pulse frequency is required for the motor to rotate at a speed of 100 revolution per minute? So we have some formula here. Alpha is equal to 360 over ns. So we already have alpha, which is 3.6. We can calculate the value of ns here. So the value of ns will be equal to 100 step angles. Okay, then in order to calculate the how many if we have 10 revolutions, so the 10 revolution will be 10 times 360, so it will be like 3600. If I want to find the value of a number of pulses, so number of pulses will equal to 360, which is 10 revolutions, over step angle, which is 3.6, so it gives you 1000 pulses. So you need 1000 pulses in order to rotate the motor for 10 revolutions. 10 revolution means each one revolution have need for 10 bars. Okay, so I mean each one revolution, if you have 10 revolutions, so each one revolution which require 100 pulses. Then we need to find what pulse frequency. He need to find the value of fp, which is the pulse frequency is required for the motor to rotate at the speed of 100 revolution per minute. He gave you the value of n and gave you the value and needs the value of fp. So we have formula set n equal to 60 fp over ns. So you just substitute for the value of n, which is 100 revolution per minute, and the value of fp here is the missing value. Ns is there, which is already find 100 step angles. So just substitute for the value in order to find the value of frequency, which is 167 hertz. So this is how to apply these formulas. Actually, there is another example also here, which is example 5, to show the how to use all these formulas that we have in the previous slide into our applications.